Good afternoon. Now it's 3 and let me start the seminar. So welcome to AIP Open Seminar. So here are some important notices I read for. Okay, so the first part, reproduction is prohibited. And second one, reproducing all or any part of the contents is prohibited without the author's permission. And the seminar will be recorded and the video will be available on the AIP website later. And if you have any questions, you can use the Q&A tab of Zoom. And I think we can have some time for Q&A at the end of each talk. Then, so let me start the seminar. So this is AIP Open Seminar of Mathematical Analysis team. I'm Shinichi Ota, so I'm a PI of this team. And then let me first briefly explain in the activity of Mathematical Analysis team. And we started October 2017, so almost four years ago, and we work at Osaka University. And here are current members. I'm Shinichi Ota doing PI of this team, and here there are two postdoc researchers, Taichi Marugame and Masayuki Aino. So they will give talks today. And also there's one research part-timer, Tomoya Akamatsu. He is now a PhD student in Osaka University. And also there are three visiting scientists, Kotori, Takatsu, and Tsunoda. Let me a bit more introduce myself. So I'm Shinichi Ota again, and I studied in Tohoku University. And then I was in Kyoto more than 10 years. And 4 years ago, I moved to Osaka. And I am a mathematician, more precisely a geometer. And my research field is more or less differential geometry and geometrical analysis. And I'm always interested in curvature. So my work is about various kinds of curvature in various spaces. And for example, I work on Riemannian and Finstra manifolds, and also some singular spaces, metric spaces, including Alexander spaces, Kessler spaces, and also metric measure spaces satisfying curvature dimensional condition. So these spaces are some kind of singular spaces satisfying some kind of curvature bounds, curvature conditions. And in these studies, we use optimal transport theory, gradient flows of convex functions, and so on. And these tools are also used in machine learning, in information theory. And so I'm also interested in applications of these tools. Then, so mathematical analysis, the aim of mathematical analysis team is, roughly speaking, pursuing interdisciplinary researches among mathematics, information theory, and machine learning. And for example, we work on optimal transport theory. So I will mention one result in this talk. And machine learning, so this will be related to second talk by Aino. And information set geometry, so this is will be related to third talk by Marugame. And also gradient flows of convex functions and topological data analysis and so on. And so far, we are mainly working in the mathematical side of these theories, but also interested in applied side. Okay, so this is about mathematical analysis team. I would like to briefly review the following preprint by a research part-timer, Tomoya Akamatsu. So it's a new transport distance and its associated rich curvature of hypergraphs. It's available here. And this preprint is concerned with a modification of the Wasserstein distance, taking into account the structure of a hypergraph. And actually, this distance is in fact new also for all usual graphs. Okay, so let me briefly review this result. Okay. And first, I recall Wasserstein distance, and then now this is very famous, and I think many people already know about it. But let me just briefly explain it, the definition. So we consider this metric space XD, and then P of X will be the set of probability measures on X. Here, the probability means that the total mass is 1. So this. And then for two probability measures, mu and nu, we consider a probability measure pi on the product space X times X. And we call it a coupling of mu nu if it satisfies these conditions. So the first condition means that the push forward of pi to this first marginal is mu. And the second condition means that the push forward of this pi to the second marginal coincides with nu. So the marginal distributions of pi is mu and nu. So this pi somehow represents a transport plan from mu to nu. Then the Wasserstein distance is, in a sense, the least cost for transporting mu to nu. So more precisely, the LP Wasserstein distance is defined like this. So we consider the LP norm of the distance function with respect to the pi, this coupling pi, and then take the infimum with coupling pi. Okay, so as I said, this pi is regarded as a transport plan from mu to nu. And more precisely for sets A and B, a pi of A times B represents the mass transported from A to B. Okay, so this condition of coupling means that pi represents the transport from mu to nu. Then this pi of A times B represents the mass transported from A to B. And then WP to the power P is the least cost we pay for transporting mu to nu with respect to the cost function dP. So this is the LP Wasserstein distance, and the Wasserstein distance is now known to have very diverse applications, not only mathematics, but also in economics, machine learning, and so on. And already in mathematics, Wasserstein distance has many applications, like in differential geometry, and probability theory, partial differential equations, dynamical systems, and so on. Very, very diverse applications. And in machine learning, the Wasserstein distance is used as a distance between data and images. So, and in machine learning, Wasserstein distance is also very diversely applied. And then in differential in application to differential geometry, optimal transport theory gives characterizations of lower rich curvature bands. And so this is the curvature dimension condition introduced in Sturm and Roth-Villani. And Villani was awarded Fields Medal partly for this work. And then, so inspired by this theory of rich curvature using optimal transport, Olivier and Lindu Yao introduced notions of rich curvature for graphs. So graphs are one-dimensional objects, and it is in general difficult to consider curvature for graphs. But then optimal transport theory can give a good notion of curvature via curvature. Okay. Then so this is a successful theory for curvature for graphs, and then we would like to generalize this theory to hypergraphs. Then point is that how to define transport distance taking into account the structure of a hypergraph. So this is a main question we would like to address, and then let me explain a bit more about this. Okay, and so we first explain the difference between graph and hypergraphs, and everyone knows that a graph consists of a set of vertices P and the set of edges E, and edges somehow represent binary relations. So this is very simple example. So vertices is these 8 points. So there are 8 points as vertices. Then so these are edges. So if 2 vertices are connected by segment, so this means that this pair of points is edge in this graph. Okay, this is a graph. And hypergraph is a generalization of a graph, and it's again consists of a set of vertices and now hyperedges. So the hyperedge means that hyperedge is a subset of P. Okay, yes, so this E represents the set of hyperedges, and each hyperedge is a subset of the vertices, the set of vertices. So this means that in the usual graph, we consider only a pair of points as edge. But in the hypergraph, we can consider this is hyperedge of 3 points, 3 vertices, and this is hyperedge of 4 vertices. So in this way, we can somehow describe higher dimensional relations. Yeah, so this is hypergraph, and can be used to study some applied topics. Then, so how to consider transport distance in hypergraphs? So first we consider a distance function on a hypergraph. Then so we follow the case of graph. So the graph distance is defined as a minimum of the edges we have to pass from one point to the other. Then so this distance can be generalized to a hypergraph. So for example, from this point to this point, the distance is 2, so 1 and 2, and from here to from here to here, this is distance 3, 1 to 3, and we can do the same in hypergraph. From here to this point, distance is 2, like this, or maybe like this one, 1, 2. This is also possible, and from this point to this point, the distance is again 2, 1, 2, or maybe 1, 2. Okay, so the graph distance can be generalized to hypergraphs, but then we have to be careful about that. So the graph distance of hypergraph coincides with the graph distance of the quick expansion of the hypergraph. Here, the quick expansion of a hypergraph is a graph whose vertex set is the same as the original hypergraph, And the edges consists of pairs contained in some hypergraph. So here, the pair xy is an edge in this critical expansion if this set is contained in some hyper edge of the hypergraph. So this is the hypergraph in the previous slide. Then the critical expansion is like this. So about this red hyper edge, so this is triangle and we connect every pair of points by an edge. Now this is 4-point hyper edge, and we are again replace it with a complete graph. So every pair of points is connected by edge, and again this is 4-point hyper edge replaced by the complete graph, and this is also okay. Then you can see that the graph distance of G coincides with the graph distance of H. And then, so if we define the transport distance by using only the graph distance, then one cannot distinguish H and G. And it's not good in a sense. So now redefining the transport distance does not distinguish H and G. So this is a problem we want to consider. So now the main question is how to define a modification with the Wasserstein distance capturing the structure of hyper edges. More precisely, can one distinguish H and G? And then in this talk, we will give one answer modifying the L1 Wasserstein distance. And our idea is to discount the transport cost when we transport in a hyper edge. So this is just a brief explanation, and let me explain more precisely from now. Okay, and now how to discount the cost? And to discount the cost, we use a concave function. Okay, so we construct a concave function h. So here h is a non-negative function from 0, 1. It is non-decreasing and continuous and concave. And h of 0 is 0, and the derivative at 0 is positive. And in some applications, we also need to assume that the derivative is finite, but not always in some applications. Okay, so the graph of h is somehow like this. So for example, ht log of 1 plus t, so this is concave. So this is function like this. And another example is the minimum of some a and t. So this is something like this piecewise affine function. So this means that we pay cost linearly to the mass at up to some point, but after that we don't pay any additional cost. So we pay up to here linearly, but then we don't need to pay additional cost. So this is this kind of function h, and also t to the power p, and p is between 0 and 1. So this is concave function. But in this case, the derivative at 0 is infinity. So in some applications, we need to exclude this case. But these two functions are always okay. Okay, and then by using this kind of concave function, we introduce modified transport distance. And here h is a hypergraph, and to the modified distance is defined like this. So for property measures mu and nu, and for simplicity, we assume it has final support. So define WH like this. So this is a bit complicated, but we consider parts Z in a set in a space of probability measure. So each Zi is a probability measure Okay, then this path starts at mu and terminates at nu. So this path is from mu to nu. And the support of each step, the difference of each step, I mean, so Zi minus Zi minus y is included in some hyperedge. And then we consider W1, so L1 Wasserstein distance of this step, and put H here. And then we take infimum over these passes. Okay, so this one. So this is the definition of our modified distance. Okay, so by this condition, so the support of is included in some hyperedge. So each transport Zi minus y 1 to Zi is done in a hyperedge. Okay, so the difference between these probability measures is only in a hyperedge. So outside this hyperedge, they coincide. So this transport is essentially done only in a hyperedge. Then we put H to discount the cost. Then we take sum. So the discount is strong if we have bigger quantity here. So if this W1 is big, then we have large discount. So this is a modified transport distance, and we remark that this WH is not W1 even for graphs. So this notion is new even for graphs. And taking HT is T recovers the original usual L1 Wasserstein distance. So since this definition is a bit too complicated, so let me explain the effect of H in a simple example. So the concavity implies that H of S plus T is less than or equal to H of S plus H of T. So this means that, so this is cheaper. I mean, transporting S plus 1 at once is cheaper than transport S and T separately. So this is cheaper than independent transport like this. So this is the consequence of concavity. And so this means that we are forced to contract the mass as far as possible. So this is, for example, if S and T and 1/2, we have this inequality. This means that we pay cheaper if transport 1 at once than separate dividing the transport to 1/2 and 1/2. So this is cheaper. And for example, we consider this kind of transport problem. We put 1/2 here and 1/2 here. So this is the sum of Dirac mass. So then here again 1/2 plus 1/2, the sum of Dirac mass, and we want to transport this from this to this measures. Then in plan A, we transport this mass to this mass, and this mass to this mass. And to denoting by K the step of this transport, the total cost is 2K times H of 1/2. So each step we pay H of 1/2, and here K step, here K step. So in total we have 2K times H of 1/2. This is plan A, the cost of plan A. And in plan B, we consider a different way. So we first transport from this point to this point. Then we have total mass here, total mass 1 here. Then we transport this from this to here. Then finally we move 1/2 here. Okay. Then this time we transport 1/2 twice. So this and this. So two times the edge of 1/2. And here we transport total mass k step in k steps, k times h of 1. And then, so if h is very concave, this plan B is cheaper than plan A. More precisely, so B is cheaper than A if h satisfies this inequality. And this actually falls if h is concave enough. If h is concave enough, h of 1 is not so bigger than h of 1/2. But then here the coefficient is close to 2, so this is cheaper. This is smaller for very concave h. So this means that we are forced to contract the mass like this. So this is cheaper. So this is okay. So and this phenomena is seemingly natural in some practical applications, I think. However, the computation of this distance is difficult, as you can imagine. So this is I have no idea about effectively computing this distance. But so far, we could obtain some theoretical results, including the existence of an optimal path attaining. So optimal means a path attaining this distance. And also there are some related works. So the first one is the structured optimal transport by this process. So they consider a kind of discount using a concave function. But they consider this discount coupled with decomposition of the space. And the structure means that we consider transport preserving this decomposition as far as possible. It's very roughly speaking, it's such kind of transport problem. But hyper-H is not this decomposition. So I mean, in this paper, they consider disjoint decomposition of the space. But in hyper-H, in hypergraph, hyper-H's are not disjoint, so we can't directly apply their construction. And actually, the definition of WH is very different from theirs. And another related work is optimal paths related to transport problem by Shah. So this is paper in a mathematical journal. And he considered kind of minimizing problem for the trajectory of transport. And then one of the main results in this paper shows that such trajectory can be a tree. And actually, we use somewhat similar construction in his or her proof to show the tree structure when we show the existence of an optimal path. So we have some for similar construction to this paper. Okay, so this is about transport distance, and in the last minutes, I also explain about the rich curvature. Okay, so as I said, the optimal transport theory can be used to define rich curvature for graphs, and we follow that line to define rich curvature for hypergraphs using the modified distance WH. Okay. And we more precisely follow Lin-Lu Yao's construction. So now it's standard one. Okay, and now we consider hypergraph, and X is a vertices. It's a vertex for a vertex in hypergraph, and a parameter alpha. We consider random walk, so-called alpha lazy random walk, mx alpha from X like this. So this random walk stays at X, still stays at X, so probability alpha, and move to a neighboring point, move to a neighboring point in the equal probability, so in a uniform probability, and otherwise it's 0. Okay, so here dx is the degree of X, so this is a uniform distribution on neighboring points. Okay, so we consider this kind of standard lazy random walk from X. Then, okay, so the rich curvature is defined like this. So the kappa h of X and between xy of alpha and between xy is defined as 1 minus wh distance between these random walks over the wh between Dirac masses at X and Y. And here, Dirac WH distance between Dirac masses can be simply calculated like this: h of 1 times the distance between X and Y. So this one is just this one. And then the kappa h of xy is defined as the limit as alpha to 1, but of this kappa h alpha over 1 minus alpha. So this is Olivier and Lin-Lu Yao's definition of rich curvature. And here the point is that if this kappa h is positive, then just by definition, WH distance between random walks is less than the distance between the starting point, Dirac mass. So the positive curvature is something like, so we are on a sphere. So sphere is for positive curve space. In this case, after random walk, they get closer and closer after random walk. So this is like a phenomenon in sphere. So this is I think, good intuition behind this curvature. And we use limit inf, but in the original case, we can show the existence of this limit. So in the case ht is t, so we can show the existence of limit. But for general h, we cannot show the existence of limit, so we use just limit inf. And also one can calculate this kappa h for some concrete examples. I will not explain about this. Then, so by using this curvature, we can show many geometric and analytic results for graphs. And as a generalization to our setting, we can show Bonnet-Myers type theorem. This means that positive curvature implies diameter bound of the space. So more precisely, if a hypergraph satisfies the positive curvature bound, so the curvature kappa h is bounded from below by some positive constant k. Then we have diameter bound. The diameter is bounded above by 2 over k times this coefficient. And here the diameter is just a supremum of the distance function. So this hypergraph is finite bounded under positive curvature condition. And we remarked in the original case, the diameter bound is given by 2 over k. And here, this coefficient, h derivative of h at 1 over h of 1 is less than or equal to 1. So in this sense, this estimate improves the original case, HTST. So this constant is, coefficient is less than or equal to 1. And one can also estimate the number of vertices, so a kind of volume. Okay, so this is an application of the rich curvature by using WH. Okay, then and finally we summarize and give some open questions. So we defined a transport distance capturing the structure of hyper-H. Actually, we could distinguish hyper-H and its clique expansion, and also this distance is new even for all graphs. But still, I wonder that if any other such transport distance. So this WH is seems natural in a sense from theoretical viewpoint. But for example, about computation, this is not a very good notion. So I wonder if there is any other good transport distance capturing the structure of hyper-H's. Again, and we showed then the Boneless theorem. So in terms of the rich curvature associated with the modified Waterside distance WH. And in the original case, there are many other analytic and geometric applications of rich curvature. So we would like to have further applications of this coverage. So this is also a future problem. Okay, so this is so this talk is based on this reprint by Tomoya Akamas, and I stop here. And now I see one question from Emerson Escara. So let me read his question. So in the random walk M alpha X, you define as some sort of limiting probability measure of the random walk, letting it run forever. So I'm not sure about. So I think let me just recall the definition. So this is just one step random walk. We consider just one step random walk. Then so this curvature is concerned with just the difference of Waterside distance in part one step. So after one step, we get closer, then the curvature is positive. So this is the idea. So if the curvature is negative, this distance is bigger than the original distance. So these other walks are faster. So is this okay? Okay. Then I think now it's just time. So I stop here, and maybe after a few minutes break, the second talk by Haino-san will start. So thank you. Okay, then I think we can start the second talk by Masayuki Haino. So please start.
Thank you for this opportunity, and let's start. The title is Self-Tuning Laplacian Eigenmaps and Conformal Metric Compatible with a Measure. Let's start. The Laplacian eigenmaps is one of the dimensionality reduction, and dimensionality reduction is one of unsupervised learning. Given data is the data is given in high dimensional Euclidean spaces, and some transformation, by some transformation, we get corresponding data, corresponding output in relativity lower dimensional Euclidean space. One of famous method of the dimensionality reduction is principal component analysis. Algorithm of principal component analysis is as follows, but this is out of focus of this talk. I do not go in detail, but for principal component analysis, the transformation map is given by a fine map like this. So PCA is linear dimensionality reduction. In this talk, we consider the non-linear data like this, and we want to get some data in lower dimensional spaces like this. This kind of by manifold learning, we get lower this kind of lower corresponding data in lower Euclidean space. To get this, I used the algorithm described in this talk. The method is the main focus of this talk is Laplacian eigenmaps. Laplacian eigenmaps is one of the methods of nonlinear dimensionality reduction manifold learning, and the transformation map is given by eigenfunction of Laplacian, like this. Here, eigenfunction of Laplacian. Here, Laplacian is defined as a minus trace of Hessian, and eigenfunction is the of Laplacian means the solution of this differential equation. The transformation map is given by these functions, these functions. For example, eigenfunction on the circle is given by 1 and cosine I theta and sine I theta. This is a complete set of the eigenfunctions on S1. Here, the circle is parameterized by angle like this, and the Laplacian is given by minus of the second derivative about theta. We can give expansion of the function by these eigenfunction. For S1 case, for circle case, this is known as the Fourier series expansion, like this. And we can embed S1 by these functions, these eigenfunctions. Here, cosine and sine is lowest non-trivial eigenfunction of S1, and cosine and sine is identity map. In particular, this is embedding function. Let's consider the general closed manifold. MGP closed means compact and without boundary. Riemannian manifold like this, sphere and torus and so on. For simplicity, we normalize the eigenfunctions as like this. Then we get the generalization of Fourier series expansion for general general closed Riemannian manifold like this. We can give expansion of function by eigenfunctions fi. Here fi is eigenfunction of the Laplacian. In particular, if we have some embedding map from M to some Euclidean space, then this embedding map is can be approximated by eigenfunction, because we can approximate any f with appropriate regularity. So for sufficiently large D, the series F1 to Fd is an embedding, topological embedding. And moreover, some authors give the upper bound of the embedding dimension D here by several geometric parameters. However, in this talk, we focus on the approximation of the eigenfunctions rather than its properties. We focus on the approximation. To approximate the eigenfunction, I describe the k nearest neighbors set first. Given data x1 to xn, and choose parameter k, and reorder x1 to xn by nearest one, nearest order. Then k nearest neighbor set for xi is defined by like this. The most nearest one is xi1, and case nearest one is xik. Then the Laplacian eigenmaps proposed by Belkin and Nyogi is the algorithm of the Laplacian eigenmap is as follows. We are given data x1 to xn and choose parameters t and k and embedding dimension d. Then the matrices k, d, l, we define matrices k, d, l like this using the kernel function. Here, we choose the kernel function as exponential. Then solve the eigenvalue problem of this form. And eigenvalue, then using the eigenvalues of this eigenvalue problem, the corresponding data in lower dimensional Euclidean space is given like this. This is output of Laplacian eigenmaps. I next introduce the self-tuning Laplacian eigenmaps. This self-tuning method is proposed by Zelkin, Maynard, and Perona. The difference is here, the kernel function, and the previous one, we need to choose the parameter t. However, we don't need to choose the parameter t here. And t is replaced by the distance, k nearest distance like this. And the remaining part is the same as the previous one. this V1 to PD approximates the eigenfunctions of the Laplacian and the approximation result is given by several authors like this. I first explain assumption of the approximation. I first define the concept of the reach. For given submanifold, we define reach by like this. Reach is defined by defined so that infimum of there exists two point more than 2 point nearest points like this. So for S1, the reach is 1. For S1 with radius 1, the reach is 1. And for this kind of object, the reach is 0 because there is 2 point nearest. There is 2 nearest point for this. There is 2 nearest point for this point, and there is also 2 nearest point for this point, and so on. So the reach is 0 for this subset. And we can bound the operator norm of the second fundamental form by reach like this. And so sectional curvature and injectivity radius is bounded like this. So the bound on reach gives intrinsic bound of several geometrical parameters. So the assumption reach is very strong assumption. I next explain some our sampling condition. In this talk, we assume that data is taken from probability measure on the manifold of the form like this. And the density function rho is a Lipschitz function and satisfies this one. For notation, mu n denotes the product measure on n times of m. We consider this form probability measure. And when n goes to infinity, the continuum limit of the Laplacian eigenmaps, self-tuning Laplacian eigenmap is given by as follows. The continuum limit is not Laplacian of the mg itself, but some the Laplacian of the conformal metric on M. Here, this conformal metric, the Laplacian of this conformal metric is given like this. Here, G is Riemannian metric on M as a submanifold, and and Laplacian G is Laplacian on Mg itself, and the continuum limit is the Laplacian on the conformal metric G tilde. for G tilde, we have the Riemannian volume measure on mg tilde. It coincides with the probability measure mu. So this G tilde is compatible with the measure. This is our continuum limit. And our choice of parameter k, which is like this. Square root of n log n, or k is almost equal to square root of n log n. Next, recall the self-tuning Laplacian eigenmap xi x1 for given data x1 to xn. Xi denotes the k nearest neighbor set, and some matrices are given by. Then we solved the eigenvalue problems of this form. Then we can give the approximation result like this. Essentially, this result says with the previous parameter choice, with probability at least 1 minus n minus gamma. Here, n denotes the sampling number, and with probability at least 1 minus n minus gamma, we get the approximation of the eigenvalue of the conformal metric like this with rate, with this rate. Here, alpha m is defined like this for normalization. For eigenfunctions, a similar result holds. Before explaining the approximation of the eigenfunction, we need the concept of the spectral gap. For eigenvalue of the Laplacian, we define the spectral gap delta lambda like this. This is smallest difference of the such that in like this. Here, lambda L is not equal to lambda J. Delta lambda is defined by minimum of this form. Then similar result for eigenvalue with the same rate, but here the spectral gap up here the spectral gap appears, and uj is the eigenvector for our eigenvalue problem, and fj is eigenfunction of the Laplacian for conformal metric, which is normalized as this. And here, normalization factor is beta m, defined by this. So we can approximate the eigenfunctions by our Laplacian eigenmaps. Let us give some remarks. One can prove these are approximation results by combining methods of these authors, except for m equal to. After getting this result, I found these papers, but and combining these results, these methods, we get these results, except for m equal to. For m equal to, the convergence rate by this method will be this one. And but the choice of the parameter k is different from ours. And choosing k like this for sufficiently large C1. And in this talk, we consider normalized graph Laplacian, but they consider the unnormalized graph Laplacian, and they get this kind of approximation result, assuming rho is C2 alpha regularity. But our choice of k is independent from the intrinsic dimension. But for this, the choice of k, for choose k, we need to know the intrinsic dimension m previously. And this convergence rate is better than ours for m is bigger than 5. But for example m equal to, then this is better than this. For the proof, they use the optimal transport distance between the given measure and experimental measure, like this. To relate discrete and continuous object. But a more direct use of Bernstein equality, we can improve the convergence rate for m equal to. This is their rate, and this is our rate. The logarithmic term is a little bit better. Next, I explain the interpretation of the method. Let iota be a conformal embedding. That is, the pullback metric is conformal to G tilde here. G tilde is Riemannian metric, a given Riemannian metric on M, and pullback metric is conformal to G tilde. let us assume that the samples x1 to xn is taken uniformly from the volume measure on M for G tilde. Then the self-tuning Laplacian eigenmaps approximates the spectrum of G tilde using the image iota x1 to iota xn. Image in the right picture. By iota is not necessary distance preserving, but we assume conformal. Then we can get the information of the spectrum of the G tilde by using the samples obtained in the image. Here, if we do not assume the conformal assumption, there is infinite dimensional degrees of freedom in the choice of metric G, such that volume capital G is equal to volume tilde G without the conformal assumption. So one cannot recover the spectrum from the data points in the image without conformal assumption. I next give example of the calculation of our eigenvalues. I first consider the standard sphere. I first consider the uniform measure, that is the Riemannian volume measure on S2, and x1 to xn, the sample x1 to xn is taken uniformly, but randomly. The true value should be like this. Our using our method, the result is like this when n is 10,000, and n is and for n is 40,000, we get this this result. The first 8 eigenvalues. I calculated the first 8 eigenvalues. I next consider the conformal transformation on S2. There is conformal transformation map FT defined by this. This is the conformal transformation on S2. And thus FT is conformal embedding. And consider samples x1 to xn in S2 uniformly, but we consider the image of these samples ftx1 to ftxn. Then ftx1 to ftxn is not uniformly on S2, but probability measure with some density. But our method, our result shows that by these samples, by these given samples ftx1 to ftxn, we can calculate the eigenvalue of the Laplacian on S2. These are the result. The true value of the eigenvalue of the Laplacian on S2 is as follows as the previous one. And we choose t equal 1.5, and the sample number is 10,000. Then the result is like this. And if we choose t equal 2, then we get like this. So t is if t is far from 1, then ft becomes far from the identity map. So the density has bias, more strong bias for t equal 2 than t equal 1.5. Yes. With uniform sampling, I answer the question. Uniform sampling, with your uniform sampling, we get the convergence to the Laplacian of the original metric. Yes. I answered the question. Okay. Thank you very much to ask the question. And the future work. For the future work, the assumption reach is very strong assumption, and implies very strong intrinsic bounds. So want to weaken the assumption to allow to posit some singularities. So for this purpose, the assumption reach is too strong. To weaken the assumption, as a first step, we consider, I'd like to consider the following assumptions. Note that the bound on reach implies these assumptions, but because the reach gives intrinsic bounds of several geometrical parameters. But weaker assumption, to considering these weaker assumptions, the limit space, we can approximate some submanifold with some extrinsic singularities. We can approximate submanifold with some extrinsic singularity by smooth manifold, satisfying these assumptions. There is several examples. So as a first step, I'd like to consider these assumptions. Okay, this is the final page, and I stop here.
Okay, so thank you for talk. And are there any other questions or comments? You can use the Q&A tab if you like. So it's okay. If not, actually it's it's a time for the start talk. So Marugami-san, would you please start?
Okay, I've I would like to talk about Boneless theorem for statistical manifolds. So first, I'd like to introduce myself briefly. So I'm doing pure mathematics, and my research interest is differential geometry. And in particular, I'm doing CR geometry or Cauchy-Riemann geometry, and conformal geometry, and projective differential geometry. And these geometries are called so-called parabolic geometries, and there is a unified method to deal with these geometries. And I'm interested in differential invariants, invariant differential operators, and natural curves in these geometries. And recently, I'm also interested in information geometry. In particular, I'm interested in its relation to parabolic geometries. And also, I'm interested in the embedding problems of statistical manifolds. And actually, today's talk is about some embedding theorem for statistical manifolds. So in this talk, we establish the Boneless theorem for statistical manifold. So what is Boneless theorem? So this is originally a theorem about isometric embedding of a Riemannian manifold into the Euclidean space. And we want to prove analogous theorem for statistical manifolds. So let me start with the review of the Boneless theorem in Riemannian geometry. So first, we introduce some extrinsic curvature quantities defined on a Riemannian submanifold in the Euclidean space. So let Mg be an n-dimensional Riemannian submanifold in the Euclidean space of dimension n plus r. So r is the codimension. So we always work locally, so we take local orthonormal frame nu1 to nu-r for the normal bundle of n. Then we have the orthogonal decomposition of the restriction of the tangent bundle of the Euclidean space to M into the tangential part and the vertical part. So vertical part is the normal bundle, and we trivialize the normal bundle by using this local orthonormal frame. So RR is the trivial bundle of rank R over M. Okay, and we also have the orthogonal decomposition like this. And so for X and Y vector fields on M, let D be the canonical flat connection on the Euclidean space and consider the derivative dxy. Then this may be no longer tangential to M, so we decompose it according to this orthogonal decomposition. So the tangential part agrees with nabla xy, where nabla is a Levi-Civita connection for the metric G. And we denote the component of orthogonal part by HAXY. Then this becomes a symmetric form on M, and this is called the second fundamental form. And similarly, we decompose dx nu A, and the tangential part is denoted by SAX. And SA is an endomorphism over Tm, and this is called the shape operator. And we also denote the vertical part by tau ABX. So we have three kinds of tensor quantities induced by this embedding. And actually, this shape operator and the second fundamental form are closely related. And actually, they satisfy this relation. So this means that if you lower the index of the shape operator by using the metric G, then it agrees with the second fundamental form. So they are essentially the same object. And also we can show that tau is skew symmetric in the index A and B. So if the codimension R is equal to 1, then this tau should vanish. So if M is the hypersurface in the Euclidean space, you don't have this tau term. Then these extrinsic quantities satisfy certain equations called Gauss-Quadrature equations. This is derived from the flatness of the ambient connection, capital D. And there are three kinds of equations, and these are algebraic and differential equations. The first one is the Gauss equation, and this means that the Riemann curvature tensor of G can be expressed in terms of the second fundamental form. And the Quadrature and Rich equations are differential equations for H and tau. And here, the bracket means the skew symmetrization over the indices. And we remark that if the codimension R is equal to 1, we know that tau is equal to 0. So we don't have these three terms. And also this term automatically vanish. So the Rich equation becomes vacuous. And we only have the Gauss-Quadrature equations. And we can also omit the index A because it has only one component. So we have the Gauss equation, the Quadrature equation like this. And this is the classical Gauss-Quadrature equation in the hypersurface theory in Riemannian geometry. So if you have a Riemannian submanifold in the Euclidean space, then you have some tensor quantities H and tau, and they satisfy these Gauss-Quadrature equations. And the Boneless theorem asserts that actually the converse is also true. So this is the Boneless theorem in Riemannian geometry. So if an n-dimensional Riemannian manifold MG admits certain tensors H, tau with these symmetries, which are satisfying the Gauss-Quadrature equations like this, then it is locally isometrically embeddable to the Euclidean space of dimension n plus r. So if you're given an abstract Riemannian manifold, and if you can find some tensors H and tau satisfying the Gauss-Quadrature equations, then you can embed it into the Euclidean space isometrically. So this is a Boneless theorem in Riemannian geometry. And we want to consider a statistical analog of this theorem. So first, I will give the definition of the statistical manifolds or statistical structure. So let M be a C-infinity manifold. Then we say a pair G nabla is a statistical structure on M if these conditions hold. The first, G is a Riemannian metric on M. The second, nabla is a torsion-free affine connection on M. And G and nabla must satisfy the condition that nabla G is a totally symmetric three-tensor. So this is the definition of the statistical structure. So you have a Riemannian metric and a torsion-free affine connection, and they must satisfy a certain compatibility condition. So for example, if you take nabla to be the Levi-Civita connection of the metric G, then you have that nabla G is equal to 0. So in particular, this is totally symmetric, so this becomes a statistical structure. So a Riemannian manifold can be considered as a special case of statistical manifold. And in other words, the statistical structure is certain generalization of a Riemannian structure. And in information geometry, the statistical structure naturally appears as a geometric structure on spaces of probability distributions. So for a family of probability distributions parameterized by a manifold M, you can define the inner product Gxy by the expectation of x log p times y log p. So this is positive semi-definite symmetric form. And if this becomes positive definite, we call it the Fisher metric on this family of probability distributions. And we can also define the connection nabla by this expectation. Then the pair G and nabla becomes a statistical structure. So in many cases, for many family of probability distributions, you can define a natural statistical structure. So this is the origin of the name statistical structure. And if you have a statistical structure on a manifold, then you can also define the dual statistical structure on the same manifold. So let G be a Riemannian metric and nabla be a torsion-free affine connection on manifold M. Then we have the dual connection of nabla denoted by nabla star. And this is defined by this equation. So this equation uniquely determines an affine connection nabla star. So for example, if nabla is a Levi-Civita connection of the metric, it is self-dual. Then actually, the condition that nabla G is totally symmetric is equivalent to saying that nabla star is also torsion-free. So this is another characterization of the statistical structure. And this gives a geometric meaning of this somewhat mysterious condition. So in particular, if G nabla is a statistical structure, then G nabla star also becomes a statistical structure. And this is because nabla star is torsion-free, and the dual connection of nabla star is nabla, so it is also torsion-free. So both nabla star and nabla are torsion-free, so this becomes a statistical structure. And this is called a dual statistical structure. And next, we defined a flat statistical manifold. So in the Boneless theorem, we consider the embedding of a statistical manifold into a flat statistical manifold. So we have to define what is flat statistical manifold. So a statistical structure G nabla is called flat if nabla is a flat connection. That is, the curvature tensor vanishes. And if G nabla is a flat statistical structure, then G nabla star is also a flat statistical structure. So this is also called a dually flat structure. And this is because their curvature tensor are related by this equation. So if one of them vanishes, then the other also vanishes. And in this definition of flat statistical structure, we assume that nabla is a flat connection, but we do not assume that G is a flat metric. So the metric G is not necessarily isometric to the Euclidean space. But actually, the condition that nabla G is totally symmetric imposes some restriction to the metric G, and I will explain about it. So suppose G nabla is a flat statistical structure, and let X be affine coordinates for nabla. So affine coordinate means that the Christoffel symbols all vanish. So if nabla is flat, you can always take such coordinate system, and it is unique up to affine transformations. Then it follows from the condition that nabla G is totally symmetric, and the Poincare lemma that we can locally write the metric as the Hessian of a function psi in this coordinate system. And such a metric is called a Hessian metric. So if G nabla is a flat statistical structure, then G must be a Hessian metric in some coordinate system. And actually, the converse is also true. So the notion of flat statistical manifold is equivalent to the notion of Hessian manifold. So the metric has a very special form, but it is not unique. You have a freedom to choose the Hessian potential psi. So this is a very big difference from the Riemannian geometry. In Riemannian geometry, flat metric is always isometric to the Euclidean metric locally. So the local structure of flat Riemannian manifold is essentially unique. But unlike Riemannian geometry, the local structure of flat statistical manifold is not unique. It is given by the Hessian metric. So this is the difference from the Riemannian geometry. Okay, we need one more notion. It is statistical submanifolds. So let SGD be a statistical manifold. So the capital G is a Riemannian metric and capital D is a torsion-free affine connection. And suppose that M is a submanifold in S. Then we can define the induced statistical structure G nabla on M. And it is defined as follows. So first, the Riemannian metric G is defined by just the restriction of the ambient metric capital G. The second, the connection nabla is defined by this equation. So this means that nabla is given by the orthogonal projection of capital D. So you consider the derivative dxy and you project it to M. So if you define the connection like this, then it is automatically torsion free. It follows from the torsion freeness of the capital D. Then the pair G nabla actually becomes a statistical structure. And this is because the dual connection of nabla star, is given by the orthogonal projection of capital D star, the dual connection of capital D. So capital D star is also torsion free. So this nabla star becomes also torsion free. So since both nabla and nabla star are torsion free, G nabla becomes a statistical structure. Then we can pose a natural problem about embedding of statistical manifold. So the problem is the following. When is a statistical manifold MG nabla embedded to a flat statistical manifold? So in Riemannian geometry, it is natural to ask when is a Riemannian manifold can be embedded to a Euclidean space. So this is an analogous question for statistical manifolds. And actually, the answer to this question was already given by Hong Van De. And she showed that any statistical manifold can be locally embedded to a flat statistical manifold of sufficiently large dimensions. So you can always embed a statistical manifold to a flat statistical manifold if the dimension of the target flat statistical manifold is sufficiently large. And this is a statistical analog of Nash embedding theorem. And in this talk, we consider a statistical analog of the Boneless theorem. So this is another type of embedding theorem. So in Boneless theorem, you fix the dimension of the target flat statistical manifold. And instead, we assume the existence of certain tensor quantities which satisfy the Gauss Quadrature equations. So in order to formulate the Boneless theorem for statistical manifolds, we first need to introduce extrinsic curvature quantities defined on statistical submanifolds in a flat statistical manifold. So this is exactly the same procedure as in Riemannian geometry. So let SGD be a flat statistical manifold of dimension n plus r. So in this case, capital D is a flat connection. And let MG nabla be a statistical submanifold. So G nabla is the induced statistical structure. Then we again take the local orthonormal frame nu1 to nu-r of the normal bundle of M. And we again decompose the restriction of the tangent bundle S into the tangential part and the vertical part. Then the derivative dxy is decomposed into nabla xy and the second fundamental form. And we can also decompose dx nu a into the shape operator, which we denote by h star a, and the vertical part tau a bx. So in the Riemannian case, we denote the shape operator by S, and it was essentially the same as the second fundamental form. But for the statistical manifolds, this shape operator does not coincide with this second fundamental form. And we denote it by H star instead of S. And this is because actually this H star agrees with the second fundamental form for capital D star, the dual connection of capital D. So you can replace this capital D by capital D star because capital D star is also flat. And if you decompose the D star xy into tangential part and vertical part, then the second fundamental form agree with this shape operator. So this is kind of dual to the original second fundamental form. So we denote it by H star. Then we again have the Gauss Quadrature equations derived from the flatness of capital D. So this is the same as in Riemannian geometry. And we have Gauss equation and Quadrature equation and Rich equations. So in this case, we have two Quadrature equations. So this is quite similar to the Gauss-Quadrature equations in Riemannian geometry, and it is not surprising because these equations are derived from exactly the same computation as in Riemannian geometry. And actually, the Riemannian Gauss-Quadrature equation can be considered as a special case of this equation. So if you take S to be the Euclidean space with the standard metric and the standard flat connection, then the induced connection agrees with the Levi-Civita connection of G, and H agrees with H star, and we recover the Gauss-Quadrature equations in Riemannian geometry. So this is a generalization of the Gauss-Quadrature equations in Riemannian geometry. Then we have the following Boneless theorem for statistical embedding. So let M G nabla be an n-dimensional statistical manifold. And if M admits certain tensors H, H star, and tau, which satisfy the Gauss-Quadrature equations, then M can be locally embedded to a flat statistical manifold of dimension n plus r. So this is the Boneless theorem for statistical manifolds. And this is an exact analogy to the Boneless theorem in Riemannian geometry, but actually there is some difficulty in proving this theorem. So as I already said, the local structure of flat statistical manifolds is not unique. It is given by the Hessian manifolds. So due to this, you cannot apply the method which is used in the proof of Riemannian Boneless theorem. So in order to overcome this difficulty, we use another notion of statistical embedding, which was introduced by Laplacian. So there's another notion of statistical embedding. And in order to prove the Boneless theorem, we first establish that the embeddability into a flat statistical manifold is actually equivalent to the embeddability in the sense of Laplacian. So we introduced the statistical embedding in the sense of Laplacian. So in this embedding, the target space is not a flat statistical manifold, but the product of a real vector space V and its dual space V star. Okay, let MG nabla be a statistical manifold and let V be a real vector space of dimension capital N. Then a pair of embeddings F and phi. So F is an embedding to V and phi is an embedding to V star. And this pair is called a statistical embedding in the sense of Laplacian if the following two conditions hold. So the first one is about the metric. So we consider the natural pairing between xf and y phi. So xf, this is a derivative of f by x. So this is a v-valued function on M. And y phi is a v star valued function on M. And we take the pairing. Then the condition is that this agrees with the inner product of x and y with respect to the metric G. And the second condition is about the affine connection nabla. And we consider the pairing of x, y, f, the second derivative, and z phi. Then the condition is that this pairing agrees with the inner product of nabla x, y, and z. So this is the definition of the statistical embedding in the sense of Laplacian. Then a key theorem for the proof of Boneless theorem is the following. For a statistical manifold MG nabla, the following are equivalent. First, M can be locally embedded to a flat statistical manifold SGD of dimension capital N. The second is M can be locally embedded to a V times V star in the sense of Laplacian, where the dimension of V is capital N. So this capital N is equal to this capital N. So there are two notions of statistical embedding, but actually they are locally equivalent. So if you So in order to prove the Boneless theorem for statistical manifold, it is sufficient that we construct a statistical embedding in the sense of logarithm. And in that case, the target space is fixed. It's V times V star. So the local structure is unique. And in this case, we can apply some standard technique to prove the Bonnet type theorems. Okay, I will give the sketch of the proof of the Bonnet theorem. So let MG nabla be a statistical manifold, and let HH star tau be tensors with Gauss Quadrature equations. And we want to construct a statistical embedding in the sense of logarithm. So first, we construct some vector bundle over M and flat connections over it. So we set the vector bundle E to be the direct sum of the tangent bundle of M and the trivial bundle of rank R. Then we define the connections nabla and nabla star on E by these equations using these HH star and tau. So here, so we recall that if M is a statistical submanifold of a flat statistical manifold, HH star tau are induced by the ambient flat connection, and the Gauss Quadrature equations are the consequence of the flatness of the ambient connection. So here we are trying to reconstruct the vector bundle, which corresponds to the restriction of the ambient tangent bundle and the connection induced by the capital D and capital D star. Then, so if we define connections like these are flat by the Gauss Quadrature equations. Actually, they are equivalent. Then we also define the fiber metric on E, the capital G, by this equation. So for the first component, we use the Riemannian metric G on M. And for the second component, we use the standard inner product. Then it turns out that with respect to this fiber metric capital G, this bold nabla and bold nabla star are dual to each other. This follows from this explicit formula. Then, so since nabla is a flat connection, locally we can take a parallel frame EI with respect to this connection. And we trivialize the vector bundle E by using this parallel frame EI. And let capital phi be the local trivialization. Then by using this capital phi, we consider the Rn plus R valued one form theta on M, defined by this formula. So we first consider x0. So this is a section of E, and we send this by this trivialization. Then this becomes an Rn plus R valued one form. Then actually it turns out that this theta is a closed one form. So locally you can express theta as a differential of a map from M to Rn plus R. Okay, so locally one can write as theta is equal to GF with some map F from M to Rn plus R. So we take V as the Rn plus R. And we can do the same construction for nabla star. So similarly, by using a local parallel frame EI star with respect to nabla star, we define the one form theta star, which can be expressed as d phi with some function phi from M to Rn plus R. And we identify it with the dual space to V. So we have two maps, F and phi. And here we can take these frames so that the inner product of EI and EJ star with respect to the capital G is equal to the canonical delta. And this means that EI and EJ star are dual to each other with respect to fiber metric. And this is because, so EI is parallel with respect to the connection nabla, and EJ star is parallel with respect to the connection nabla star. And nabla star are dual to each other with respect to this fiber metric. So this becomes a constant function. So if you take EI and EJ star, so that this equation holds at one point, then it holds everywhere. So we can take such parallel frames. Then we can show that actually the pair of this F and phi becomes a statistical embedding in the sense of logarithm. So first we check the condition on the metric. So let X, Y, Z be vector fields on M, and consider the pairing of XF and Y phi. Then X phi agrees with theta X, and this is because theta is equal to DF. Okay, and similarly, Y phi is equal to theta star Y. And then this pairing is equal to the inner product of X0 and Y0 with respect to the fiber metric capital G. And this is because, so theta X is a trivialization of X0 with respect to the frame EI, and theta star Y is the trivialization of Y0 with respect to the frame EJ star. And since EI and EJ star are dual to each other, this standard pairing corresponds to the inner product of X0 and Y0 with respect to capital G. And this agrees with small g xy. And this is by definition of capital G. So we only have the first component, so this becomes gxy. So the condition on the metric is satisfied. So we next check the condition on the connection. So we consider the pairing of xy phi, xyf, and z phi. Then this is the pairing of x theta y and theta star z. And so in this trivialization, the derivative by x corresponds to the covariant derivative by x. And this is because EI is a parallel frame with respect to nabla. So the differentiation becomes covariant derivative on E. So this becomes inner product of the nabla x, y0 and t0. And you can compute this covariant derivative by using a definition of this bold nabla. And you can get here, you can get this. And again, by the definition of the fiber metric capital G, we have that this agrees with the inner product of nabla x, y, and z. So the condition on the connection nabla is also satisfied. So it follows that if the pair f and phi becomes a statistical embedding in the sense of logarithm, and since the embeddability in the sense of logarithm is equivalent to the embeddability to a flat statistical manifold, you can also embed M into some flat statistical manifold. So we obtained the Boneless theorem for statistical manifold. Okay, I stop here. Thank you for your attention.
Thank you for the talk. And are there any questions or comments? You can use Q&A tab of Zoom. So I have one question. So do you have any future problems related to this kind of topic?
Future problem?
Future problem.
So, okay, in this theorem of Hong-Van Le, actually, she proved more than this result. And so she showed that any statistical manifold can be locally embedded to some flat statistical manifold of sufficiently large dimensions. But actually, they embed a statistical manifold to to a flat statistical manifold, which is defined on some probability distributions. So in my theorem, the target flat statistical manifold is just abstract statistical manifold, but actually she showed that you can embed any statistical manifold into some statistical manifold, which is realized as the probability distributions on some space. So called the statistical model. So possibly the future work is to prove the Boneless theorem for the embedding to some statistical model instead of just abstract flat statistical model. So that is the future question.
I see. Yes, and are there any questions or comments? Okay, so if not, I think we stop the seminar, and we can share the schedule of the forthcoming open seminars. Okay, so this is the forthcoming schedules of the open seminar. So today's seminar was very mathematical, but usually it's more applied like big data, natural language, neuroscience. And so also if you are interested, you can find the information here. So thank you for your attendance, and I think we stop the seminar, finished seminar.